So this presentation is on Module 3. We're going to be looking at Graham's law and purification of gases, as well as van der Waals equation and non-ideal gas behavior. Graham's law states that the rate of effusion of a gas is inversely proportional to the square root of the molar mass of a gas. Effusion is how fast gas molecules can escape from a container through a tiny hole. If we take this box and let's say it's filled with helium gas, the rate at which helium leaves the box through the pinhole is the rate of effusion of helium gas. Diffusion, on the other hand, is movement of material from an area of high concentration to an area of low concentration. So what does this mean? Well, the heavier a gas molecule is, the slower it will move, and the lighter a gas molecule is, the faster it will move. So the heavier a gas is, the slower its rate of effusion. The equation for Graham's law is rate of effusion of substance 1 over rate of effusion of substance 2 is equal to the square root of the molar mass of substance 2 over the molar mass of substance 1. So let's do it. It takes 6.31 seconds for a sample of krypton to effuse from one compartment into another at a certain temperature. Determine the time it takes for an equivalent sample of neon to do the same job. So we know that as molar mass increases, rate of effusion decreases, because heavy gas molecules move slower and take longer to effuse out of container, and vice versa for lighter gases. This means that as the rate of diffusion decreases, the time it takes for a material to effuse out of container increases. Molar mass is therefore directly proportional to the square root of the time. Here we'll have neon as T2 and krypton as T1, and on this side, neon will be molar mass 2 over krypton, which is molar mass 1. The time it takes krypton to effuse out of container is 6.31 seconds, and we're solving for neon, so we'll leave that as the variable. Then we'll fill in the molar masses for neon and krypton using the periodic table, and we get a molar mass of 20.18 for neon and a molar mass of 83.8 for krypton. If you divide 20.18 by 83.8, you should get 0.2408. And now let's square the root of that. You should get 0.4907. Using cross multiplication, you times the time of neon by 1, and then you times 6.31 by 0.4907, and you'll get 3.096 seconds. That's how long it takes for neon to do the same job. Logically, this makes sense since krypton is a heavier molecule than neon. So krypton with its molar mass of 83.8 and neon with its molar mass of 20.18 means that it will take longer for the heavier molecule to effuse out of a container than a lighter molecule. Diffusion can be used to enrich or purify a gas mixture. Multi-stage diffusion was used during World War II to enrich low isotope uranium hexafluoride. The vast majority of raw uranium is composed of the isotope uranium-238, and only 0.72% is composed of uranium-235. To get low enriched uranium, which powers nuclear reactors, it requires that uranium-235 be at least 3% of the overall abundance. One way the nuclear material can be purified is by effusion through a porous barrier, but this first requires that uranium be put into the gas phase. This can be done by reacting with fluorine to form uranium hexafluoride. Graham's law of effusion states that the rate of effusion is inversely proportional to the square root of its molecular weight. So uranium-235 will effuse more rapidly than uranium-238, and as a result, the reaction is going to proceed in a given direction, and you will end up with more uranium-235 on the right side and more uranium-238 on the left side. In this way, natural uranium is enriched with uranium-235. You'd have to do this over a number of rounds of effusion in order to purify uranium from its raw state to a low enriched state of 3%. This wouldn't occur after just one stage of effusion. Recall that when we used the ideal gas law, we made two assumptions. We ignored the volume taken up by the imaginary ideal gas molecules, and we assume that the gas molecules don't attract or repel each other. In real life, however, gases are made up of atoms and molecules that take up a finite volume, and these atoms and molecules interact with each other through intermolecular forces. One way we can look at how accurately the ideal gas law describes our system is by comparing the molar volume of our gases to the molar volume of an ideal gas at the same temperature and pressure. To be more specific, at some temperature, we can take moles of gas and measure the volume it takes up at a given pressure, or measure the pressure for a known volume. We can also calculate the molar volume of ideal gas at the same temperature and pressure and take the ratio of the two volumes. This ratio is called the compressibility or compression factor and is represented using the variable Z. For gas with ideal behavior, molar volume is the same as molar volume for an ideal gas, so Z equals 1. This graph shows us the compressibility factor as a function of pressure at 0 degrees Celsius. All gases behave ideally at sufficiently low pressure, but you see deviation set in as the pressure increases. So at a high pressure, the compressibility factor will be greater than 1. Values of the compressibility factor less than 1 signify that the intermolecular forces of attraction are largely responsible for deviations from ideal gas behavior. Values greater than 1 are found when the volume of gas molecules themselves is a significant fraction of the total gas volume. Let's explain this a bit further. If we imagine our gas molecules bouncing around in a container, the pressure we measure comes from the force of the gas molecules hitting the walls of that container. Attractive forces between the molecules will pull them closer together, which effectively slows the molecule down a little bit before it hits the wall. This results in a decrease in volume if the pressure is held constant compared to what you would expect based on the ideal gas equation. One of the simplest equations to model the behavior of real gases is the van der Waals equation. The van der Waals equation basically incorporates the effect of gas molecule volume and intermolecular forces into the ideal gas equation. A is a correction term to the pressure term, which accounts for the attractive forces between gas particles. So A adjusts for intermolecular forces. In many cases, the intermolecular forces are attractive, so they take away from the pressure. That means that the pressure of a system under non-ideal conditions is lower than we expect. B is the correction term for volume. It subtracts out the volume of a gas molecule from the total volume of a container to get a more accurate measurement of the empty space available for the gas molecules. Okay, so let's take a closer look at these A and B terms. Volume is going to be larger under non-ideal conditions than that which we calculate for the ideal gas law. So here we're taking the ideal gas law and adding a variable, x in this case, to account for this change in volume. X is going to be the number of moles times a constant. The more moles we have, the more space the particles are going to take up and the more volume we will need to be added to the ideal gas law. B is a constant that is experimentally determined. Different gases are going to have different size nuclei or different size particles, and B is the constant that accounts for that. Pressure, on the other hand, is going to be lower than expected under non-ideal conditions. So we're going to subtract a term, in this case y. Y is the number of moles of a gas divided by the volume of that gas. This is the moles per unit volume of a gas. So the higher the molar density, the more likely particles are going to come into contact with one another and attract each other, which will decrease the pressure. We times this by A, which is also experimentally determined like B and varies depending on what gas you're working with. Different gases interact with each other in different ways. So the van der Waals equation combines these two corrections so that we can look at the behavior of real gases.